topic which you all can share in. And so let us get on with it.
Okay, what I want to tell you about is computers, because they have computers all over the place and everybody's talking about them and using them and are frightened by them, or else you find them very great assistants and so forth. And I wanted to tell you a little bit about how they work, what's inside them, what the idea is, what the mechanism is, so that you can get a better idea from that of what you can expect them to do and not be able to do, and so on. So that's what we're doing. We will expose what a computer really is. Actually, the first aspect is, you see, there are many different kinds of computers. There are computers that you can put the data in by talking to it even. There are computers you have to type the data in. There are computers that get that data from the machinery of an automobile or something and compute how much they should shift the gears so they have automatic transmission, but I mean controlled by an automatic computer instead of you feeling how fast you're going and what the hill height strength is. That's called the input part of the computer. That is, the information's coming from different kinds of sources. A keyboard, a telephone, sensors inside the automobile that measure temperature or acceleration or something like that. And there's another aspect called output. For example, the thing that goes out might be the control of the gasoline in the automobile. It might be to make pictures on a TV screen that you can read or look at. It might be that it makes music and makes sounds and so forth. Now, in the part that's the input and the output, which makes computers look different, is not the part I'm talking about. There is in between the input and the output. The input is converted to some electrical form, then something's done in the computer, and it spits out another electrical signal, which is used for the output. So, for instance, in the automobile thing, the various sensors are sending electrical signals to a box, which is the computer proper, or the part of the computer that I'm going to talk about. And then in the output of this box is other electrical signals which go to control magnets or something, which turn on and off the gasoline, or else control magnets which push in and out a diaphragm very rapidly and make sounds, or controls the electrical currents running in the beam that's going all the time on the screen and makes a picture on the screen, and so on. So what we're going to talk about, which is really the computer proper, is the part in the middle. So it's sort of, we don't care where the stuff comes from, we don't care where it's going out. Now, what is the stuff in the middle? That's what's really manufactured in the computer. Of course, a real computer that's sold is advertised and is good because it's got a big screen, or it's got a small screen, or it's got a tiny keyboard that your fingers are too big to push the buttons, or it's got a big keyboard that has so many buttons on it you can't figure out which one to push. And they have advantages and disadvantages, which is not what we're talking about. We're talking about what's on the inside, the central part of the computer proper, which I'm going to call it the computer proper. But the whole computer, of course, is the real thing. So, but we'll just talk about the guts in the middle, the thinking part, if you like to imagine that computers think. But what is it? I'd like to compare it to a filing system. As a matter of fact, I'll anticipate the end. A computer is a high-class, super-speed, nice, streamlined filing system. And I'm going to start out with an ordinary, old-fashioned business filing system, and to tell you ways that you can change it and improve it and so forth until it becomes a computer. One of the miseries of life is that everybody names things a little bit wrong. And so it makes everything a little harder to understand in the world than it would be if it were named differently. Computer does not primarily compute in the sense of doing arithmetic. Strange. Although they call them computers, that's not what they primarily do. They primarily are filing systems. People in the computer business say they're not really computers, they're data handlers. All right, that's nice. Data handlers would be a better name because it gives a better idea of the idea of a filing system. There's a lot of data on cards, and you handle it. You take cards out, look at them, put them back, and so on. So that's what the computer does, and I'm going to describe first an old-fashioned filing system, and then we'll talk about how it's improved, or how it might be improved, okay? Actually, it's improved to the point of being made automatic and mechanical. electrical actually, and that's our computer. And an old-fashioned filing system is something that many of you are perhaps even unfortunately familiar with. It's a whole lot of boxes, drawers, cards and things, you know, which all have stuff, numbers, and facts on them. For example, in a business which has lots of salesmen, it may be that each salesman has a card. He has his name on it and his address, what his general salary is, what his commission rate is, how much he sold last month, and where he lives, things like that, let's suppose. And it's written on lots of cards because there's lots of salesmen in the boxes. And then the problem for a file clerk might be, for example, a boss comes in and says, would you figure out, oh, the commission rate is given on the card, like a certain percentage, and how much he sold during the month. But now you have to figure out how much we have to pay him. So what you do is you take out a card, and you look at how much he sold that month, and you look at his commission rate, and you multiply the two numbers, and you write it on the card, and put it back, and do this on card after card, okay? What does it mean? So you're taking a card, then you're looking at some things, and doing something to them, that is looking at some data on the card. The easiest way to think of it, to simplify it just a little bit, is that we have scrap paper that we can erase and use again and use again. So we take and rewrite the numbers off the card, the amounts, before, so when we're doing the multiplication, we can do it with the numbers without dirtying up the card. So we copy the numbers over, and then do the calculation, see the answer, and if the rule is to put the result back on this man's card, okay, so we write it on this card. It may be that we would like to put this on some other card, maybe cards about expenses that have to be paid or something, you see? So you'd put that somewhere else. Or perhaps, to make another example, that you would like to add together all, well, I'll forget that. You want to add together all the money to know how much you're going to have to pay out. That's another example. But they're all the same, of course, that you take the numbers from the cards and write them down and recalculate and put it back in the numbers. So you have three kinds of operations. Taking cards from places, looking at information on the card, doing something to the information on the card, writing things on the card and putting the cards back. Okay? Actually, it could be a little bit simpler. You could say you take the thing out and take the information off the card, immediately put the card back. Just save it. Now you do the calculation, and when you get the answer, you pull a particular card out that what you want to put the answer on. It may be the same man's card. But wherever you want to put the answer, you take it out, write it down, and put it back. Okay? So we have two operations. Picking up a particular card, getting data off of it, doing something to it, and then putting numbers onto cards from our scrap paper on different cards. And that's all that the file clerk does. To take another example, suppose we have figured out all the amount of money that we owe each salesman, and we would like to know how much to draw out of the bank in total. So we need the total amount of all the sales. Then we could do that by having a special card called a total card and writing 0 on there. And this is a way of I'm talking about the details of what we have to do. Everybody knows what to do. You tell the file clerk to add the numbers, but this is what you might do, or he. Was write 0 on this particular thing called total sales costs in California, and do the following. Then you take the first salesman card, you look, he's not from California. We want the total amount of money we have to spend in California salesmen, all right? Just as an example. So you put that one back. Take the next card. Is it from California? No, put it back. Next card, from California, yes. Then the next instruction is to look at how much money you owe this man and write that by adding to what's on the total card. You take the number that's on the total card and the number that's on this man's card, add them together, and write that back onto the total card, right? You're keeping the total running, see? So the next time when you take another card that has a number on it, you take the new total that you just cooked up from before. There was no trouble last time. You had to add 0, but this time it's getting harder. You add it on and put the sum back on the total card. So you see you got a kind of a steady thing. And when you're all done going through all the file, the total has been changed and changed and changed and changed, and the last thing you read is the real total of all the numbers. Okay? That's what the file clerk might do in that situation. And now we're going to try to improve the filing system, to improve it. You see, we have to have a fairly intelligent file clerk that can multiply and add and so on, read cards, get instructions from the boss and remember what they are, naturally, and know how to do all these things. Has to know where to go to run up and down and pick the cards out of the boxes, and has to read the place to find the cards and know where they are, and so on. It's a lot of stuff. Well, another one comes along. We got a new file clerk. I got a new file clerk for you. Say to the 5 times faster than the old one. Oh, well, we'll hire him. But you discover suddenly that he doesn't know how to do multiplication. Well, how in the hell is he going to handle finding the commissions by multiplication? This guy isn't any good. But he's 5 times faster, so it's very tempting. If we can only get him to be able to multiply. So what do? You send him to school? Too much wasted time. Better idea. You teach him you tell him how to multiply as follows. After all, he's very fast at picking up cards and putting them down. So he takes the cards and he looks at, say, 2 numbers. And you tell him to look at the last end of the number. One's an 8 and one's a 7. Right? Then that instruction will look at card number 78 in the multiplication file. And card number 78 in the multiplication says 56. The multiplication table, which we worked so hard to learn in school, is easy to put on a set of cards. On each card, which is labeled by a number, let's say the card number 78 or 78. The card label, I don't have to convert it to a number, a card called multiply 78. Answer 16. It is written on a card. So all he has to do is pick up the right card. He's very good at that, and he's very fast, see? So he sees the 78, take the card, 56, okay? And so it goes. He doesn't have to know how to multiply. You tell him a series of instructions, what to do exactly. You give him the instructions as to which cards to look for at what time. So when you say multiply, you don't even tell him that. You tell him, look in this box now, take that card out and write down what that one says, and so on. So you see that we can describe multiplication as a definite procedure, a precise procedure of handling numbers in a kind of a dumb way, and things that would have to be memorized are never a problem. Memorization is no problem. That's what a filing system is for. That's what cards are for. We write everything on the cards. Every damn thing you've learned for all this effort is written on a card. So with cards, we can make this fast filing clerk actually able to multiply. Of course, it's slower to have to look up each time in the multiplication table because he has no memory worth a damn for numbers, this guy. So he can't even remember that he's used the 7 times 8 55 times, but he still has to look it up again. So he's slower in the sense of the number of operations to multiply than the original file clerk was. But he's really faster because altogether he handles the cards so much faster that in spite of the fact that if there's a lot of multiplication problems, he isn't 5 times faster than the other clerk, but he might be 2 times faster because he's slowed up in the process of multiplication. So our filing clerk does not have to know how to multiply. Well, we'll get a faster one. I got another one that's 10 times faster than the last one. He can't add. No problem, right? I mean, we have an adding table too, right? No problem. Okay, he's easy. He's better. He can't add, he can't multiply, can't handle numbers at all. But he can compare, read, and check that what it says on the cards is the same. He doesn't even know that these are numbers. He sees this shape and compares it to this shape and takes the cards out according to the instructions, okay? Now, where does he get his instructions? They're in a series of cards that says, do this, then do this, then do this, you see. So we have a sequence of cards with instructions on them. He doesn't even have to remember the instructions. He's rather stupid. The first filing clerk, you could say, go get the card. That instruction meant go into room 5, open the drawer, push your fingers through the card, lift, and so forth, okay? So if you want to get the card to read it and then carry it back and write it down, you could have a list of instructions for this idiot. Instead of saying get the card, you say, look in these set of instructions, please. First instruction, walk over to the file. Second, pull out the drawer. And so forth. So all he has to do is keep track of which instruction comes after which. He's really quite stupid, but man, is he fast. Dumber, but faster. Okay, the key of it all is dumber, but faster. Right? And so what we're having is filing systems with ever-increasing speed of the file clerk, but ever stupider file clerks. Okay? And they're getting better as systems because we must file everything. Now, the last fellow that we've got in this, not the last one, but the next to the last one, is unable to remember which instruction he's on. Well, what's the next instruction? Oh, but he can add one. He knows how to change something with one. He has a little counter that he pushes a button and it goes up one, okay? So all he has to remember is the following. Push the button there's a little register that he can read, okay? It's a push, that we call it the program counter or instruction count, all right? Push the button that changes the instruction count by one. That's the only button he knows how to push. Push that, okay? That's the first instruction. Read the number there on the program counter and take that card out, that instruction number out, okay? And that says, go get this paper or transfer this or whatever it is, you see? Because we have already put all the instructions in a certain order. And then put the card back, you're finished. Read the instruction, and do the instruction, and put the card back, okay? Then the next cycle he has, push the button on the program counter, read the program counter, it's the next number, you know. But he couldn't remember, so he has it there. It's the next card, takes the next card out, and it tells him what to do next, and so on, okay? So he doesn't even have to remember where he's at, as long as he's got this one little gadget inside, which I'm beginning to think you could see could be done mechanically. That is, we can make a device that all you push a button and the number changes by one, right? In fact, so that's almost got it, but we find a very much faster, 10 times faster than this marvel, who is so stupid, but so fantastically fast, which is 10 times faster than this fellow, but he can't read letters. He doesn't know what they mean. Doesn't know what the numbers mean, okay? So how is he going to, what can he do? If he can't read anything, he can't do anything. I grant you that. I grant you that. Right? But he can distinguish two signs, one from the other, which we'll call high and low, you know? Or black and white, or 1 and 0, or mark and no mark, whatever, all right? Just, he only can read not any kind of letter, but just one little spot. Let's say we always make it red and blue, you see? Is it red or is it blue? So we make a lot of spots for him, red, blue spots. It's all he can read. What an idiot. How can we make him do anything? How can he know what an A is? Suppose we got letters. We want to write the letters for names or something like that. So we would like to instruct him in the letters for the names, you see. So instead of saying, we tell him to give a better example. By this time, because they have to use so many cards and so many files, the files have gotten larger, right? There are lots of filing cabinets in many rooms all over, and this poor fool has to be able to find the right cabinet. Now, previously, we labeled all the cabinets with the names of the sections from schmaltz to zoology and so forth here, and this is in box 34, and this is all over. It's like that places in Esalen have numbers on them and so forth. I'll show you how we could do that without only with red and blue dots on the rooms. For those particular kind of workshop people who cannot read numbers, all right? And we'll still be able to do it, and I'll show you how we'll do it. Let's do it with the Esalen rooms. It just makes it more interesting. I don't propose this as a practical device, but perhaps it is. And it goes as follows. You take the map, and you divide the rooms through the middle, and say, these are the first level red and blue rooms, okay? Then you take the red rooms and divide them in half. Let's say those are the higher part of the hill and the lower part, and say they are secondary red or blue. And the blue ones, the main blue ones, have been divided into primary and secondary rooms, like this. You know? I see that I don't have red and blue, so I'll use brown and orange. It's perfectly all right. Had I said brown and orange, it would be all right. They understand that it could be any two colors. Okay, so let's first draw, what, in yellow? A lot of rooms. Can't see the rooms, okay? I don't have enough things. So these are the rooms. We'll be all right. Let's say we had this many rooms. I've got them all laid out in a straight line, but it doesn't make any difference where they are on the map, right? We got 8 rooms. I know you got more rooms than 8 rooms, but you'll see the scheme will work just as well for any number of rooms. So what we're going to do is we're going to mark all these rooms with a black dot as a first dot. I mean a brown one, all right? And these will get orange dots. Okay? Now, of the brown dotted rooms, we think of the brown dotted rooms and we look at the next dot, which says the first half of them get brown on that dot, and the second half of those get orange, all right? And then the first half of these get brown, and the second half gets orange. Oh, you say, well, still you're so clear. Okay, now you look at the brown-brown rooms, huh? Any pair, there's a brown-brown, the brown-orange rooms, the orange-brown rooms, and the orange-orange rooms. Of the brown-brown rooms, we label this side ones brown as the first. Each pair gets the front end brown, and the other one gets orange. And lo and behold, we got 8 rooms, and with 3 little dots, each of which can only have one of 2 colors, we can identify the room. So the guy who has to locate himself and who can't read numbers, but can read whether a dot is brown or orange, will, in this system, be very easy to find his unique room. In fact, it's easy to find the room, which is different, of course, as you already know, the numbers on these rooms around here do not locate the rooms, right? But this new system, we can locate the room. The first brown tells us to kind of go over here somewhere. The next brown, swap more. Is it orange? Take that side. So the filing cabinets can be very large and have labels on them, which are like these brown dots and orange dots, but because instead of being 8, there are, say, 1,000 such rooms, it turns out you only need 10 dots to do it. 1,000,000 such rooms, there's only 20 dots. Because there's so many different combinations of brown, orange, brown for 20 long, so many ways in 1,000,000 different ways. So you'd have, that way you can label a large number of different cabinets and have a file clerk which you can only read just one of 2 alternatives and make sense of it. And so we can do it with rooms and also with the letters of the alphabet, because we take the letters of the alphabet and write them along and label them. The letters on this side of the alphabet are the brown letters, first primary brown, and the others are orange, and of those you make brown. So these could have been A, B, C, D, E, F, you know. So we could teach him a different way to write his alphabet. He's so dopey, he can only read these, but we, smart enough, to convert it. So he can be, therefore, using names and numbers, but they're written in a different code. It's like the dot-dash system of Morse, only slightly more organized. We call it ones and zeros. Brown and orange, I'm calling it. Whatever. You can only read 2 possible things, okay? So the new file clerk can only make out one of 2 alternatives at any particular spot. Of course, he has to realize he's due first the first one, and then he's up to the second one. So he first makes one choice, and then the next choice, and next choice, and according with this, and then determines the letter of the alphabet. If he has to talk to us and make an output, he's not going to be able to just put his ones and zeros. We're not going to be able to read it. So suppose he wants to say something, and he wants to put an output. You ask him for the name of the best-selling, the guy who sold the most in California, and he does it with his dots, and I'll tell you a little more about how you do that. And comes out, his name starts with an A, say, or let's say it starts with a C. Huh? Where's the C? For him, it's 3 dots and a dash, right? But he wants to print C for you. What can you do? He wanted to see it look like a C. You know? So what we have done for him is we imagine he's going to write this on some kind of a screen that we have divided into squares, okay? Like this. I should make more. And we tell him whether to mark the square or not in the electronic device with a pulse so it lights up on the screen or not, by whether it's a brown or an orange dot there. So we put a brown dot here. Well, let me first draw the C. The C is going to look like this is where the orange dots go. Okay, there's a C, all right? Not a very good C, but it's a C. If you had more dots and a finer screen, it would make a much better C. So we put all these browns and so on, and then we put into a filing cabinet, under the labeling for the third letter of the alphabet, this pattern. So when he's not working internally, which is, you can use this other system, but wants to communicate with us, we've told him how to do it. What we get for a C, by putting in the filing cabinet the list of dots that he's supposed to put out on the screen. So when he's finished looking at, we look at the little white dots and black areas, we see a shape of a C. So the hardest thing he has is communicating with us, getting the information, converting it to dots, and getting the dots back to the form that we're used to. The same thing can be done with numbers, of course. Suppose that he had only deal with numbers from 1 to 1,020, 0 to 1,023. It's a happy case where you can divide. 10 times you can divide those in half. You say a number is described by the same bunch of dots by taking the top half of the numbers or the bottom half of the numbers. I already did it with numbers. It was the numbers on the rooms. So we can use these dots and so forth to represent numbers in the same way. And now we can use a particularly stupid file clerk, and it's only useful, of course, if he's really very fast, because everything requires him to looking in his damn files all the time because he knows so little. And that's what ultimately has been developed. First of all, in order to get up speed, instead of having to get up and walk over to the file, we put the files not on cards, but on little tape decks, little tape decks, electrical. And we send the signal, turn on the tape deck and listen to the signal that comes out. We don't have to run over there. We got a telephone, so to speak. We tell which one to go off, and it sends back what's on that tape. So you see that we can file things not on pencil and paper, but with electrical signals or magnetic, different kinds of techniques there are for electrically saving information. And it turns out you can do that smaller and smaller until the filing cabinet is this big, which contains millions of items. And what you're doing is you're signaling to the different filing cabinets. Depending upon the ones and zeros, there are switches inside that tells which one it goes to. And the information comes in and out electrically. That's much faster than carrying cards around and running around in sneakers. And so that's the way that's done. And by the time we got a file clerk this stupid, we can do it mechanically. We can tell whether two dots are the same. For instance, we can ask him, when the two look the same, do this. So if there's two brown ones or two orange ones, do this. Now, it's rather easy to make mechanical devices which will do things like that. For example, instead of brown and orange dots, you could have electrical voltages, which are either up or down. There's current on or there isn't. So instead of a dot of different colors, we just have a voltage or no voltage on a particular wire at a given moment. Or if you would like, but this isn't the way the electrical one is the way it's done. But if you would prefer, you could imagine you made a hydraulic computer with pipes, with pressure, with water going through. And if you look at the pipe and water's squirting out, that's a black dot. And if there's no water there, that's the other kind. So it's rather easy. So you make the pipes go squirt, squirt, not squirt. Squirt, squirt, not squirt. That's it. This one is this room. Right? Now what we need is a situation to compare things that only squirts if two things. Let's suppose we're looking for both dots be brown. Only then should you make a brown dot. In other words, two pipes such that if both pipes have water in them, then only then should water come out the other one. Well, we need only a valve operated by water. You have a pipe like this with a valve, which is a thing you turn it on, let the water through. The water's trying to go through here. It's turned off by a faucet, which only takes a small turn and has sticking out above it, instead of an ordinary handle, a flat vein, that we're going to squirt with water, and that's going to push the vein around and open the valve. So here is the things coming in with the water to operate that. So when the water goes here, it turns the water on there. Now if I put two such valves in succession in the pipe, and I had the water coming in two different pipes, then it would only work, that is, water will only come out of here if both of these pipes are squirting. Because if I got only one pipe squirting and the other not, this valve is off, but this on, so what? It don't get through on account of that's in the way. And vice versa, okay? So this is what you call an AND. You get result here when both this and that are on, then you get that on. You can do an OR just as well, where you get a result if either one is on, but that's different kind of a logic. And the way to do that is simple enough, is to arrange the pipes so that the water that's coming in is split into two possible pipes. Let me see how I draw this. Yes, well, the brown and the orange is just an accident of fate of having put the orange cap on the brown gadget. So we'll straighten that out right now. And here we go. The pipes go like this. The input is here, but we go with the two valves this way. Here's the one with the other valve, okay? And the two squirters. Let's say this one squirts here and this one squirts here. You got to get some geometry. It's three-dimensional. You got to get this pipe on top of this pipe, or there'll be trouble. Anyway, the idea is that these then come together, and you might ask, under what circumstances does water come out of there? Well, clearly, if either this is open or that's open, it either goes around this way or it goes around this way, or both. That's an OR. You get junk out only when one or the other or both is on. And so we can say very simple comparisons of these dots, or better, ones and zeros, or pressure, water and no water, or electricity and no electricity, voltage or no voltage, electrons or no electrons. And so we can make the device simple enough now that we don't need a human being anymore to do the file work, and the whole system is now a computer. It's all done electrically, and it has this kind of switches in it. Electrical valves are called transistors, and how they work in detail, how the electrons come in here affect the electrons going there, I won't describe. But just granting that a transistor is the analog of a valve, but for electric current, then you're going to understand that large numbers of transistors, lots of these valves making comparisons, switching where the current goes to find the right filing place in the box where all the stuff is filed and so forth, would constitute a computer, and that all a computer does is what a filing cabinet system can do. It can do everything that most things that an ordinary file clerk system can do. It can multiply numbers because we store the numbers. We store the combinations. It can add. It can do all these things, even though it can hardly do anything. And you might ask, is there some kind of design of computers that can do more than other kinds of computers? And the answer is no. It turns out, once you begin to understand this, that if you try to add more complicated things, you can always put them back in filing systems and use the same system to do a more elaborate thing. So all the computers can do the same things, but maybe they take longer, or it may be a matter of efficiency, but they can all do the same things. They're all universal inside, if they're big enough. Their limitations are how big is your filing system. Maybe there's not enough room for all the cards you want to put in, and things like that. But that's the only differences between the different machines. At any rate, that is supposed to be an expose of what the heck's inside the machine. Now let's ask what such a machine could do. First of all, the same machinery can be used for more than one problem by just having different instructions. Lists of instructions, what to do this, then that, to do that, to deep. And another problem, you do something entirely different. This might have been a business with salesmen and so on, and now you want to do oil company reports and listings of what they discover when they drill, all right? So all new numbers, all new instructions of how to handle numbers, everything. What do? Buy another filing system. It's more expensive to do that than to do the following. Throw away all the cards from the business company. Wait a minute, suppose you want to come back and, all right. Take everything that's on the cards of the business company and make photocopies and store them in the basement. Now erase all the cards. So if you want to come back, we'll come back. Then you go down the basement from the time last year when you were doing the oil company problem, and pick up from the photocopies all the stuff that was supposed to be on the cards for oil business. And then just fill up all the cards with the oil company's job, with the instructions for oil companies, and our dumb file clerk is now an oil company file system, okay? Because he's got new instructions. And these things that in the basement, the analogy that I want to make is that those things are dead, not operating, and are just stored. They're not easy to get at. It's hard to get down to the basement. It takes a long time to pull them up and set them in all those cards. But you do that just once in a while when you want to change a problem. When you've got them all in, then you can rapidly take them and put them in, compare them and do this, like the filing clerk is supposed to do. So we have cassette tapes or hard disks or floppy disks or various and sundry different ways of taking a large numbers of instructions out and sticking them on the disk and leaving them there, putting them in your back pocket, throwing them around in the boxes while the computer's doing something else. Then if you want to change your computer to a word processor instead of a game or whatever it is, then you just take out one disk, put the other disk in, puts new stuff into the computer, all new instructions, dumb file clerk working like a son of a bitch, and a big memory outside. And that's why computers can do so many things, apparently. The same computer. It doesn't do so many things. It always does the same thing. It follows instructions. And the instructions are very dumb and at a low level. Okay, that's the end of the expose, but I would like to make some remarks and some things about, because people like to think of things more than just how does it work. They would like to know what's the future. Why can't we improve this? Look at what we've got now. We have this enormous memory with lots of data all around, which is sort of sitting there. And this one little section where something's happening, which I called the file clerk before, which is the systems, which go and get something, pull it in here, do something over here, then put it there. Then you take something else and put it here and put it there, put it there. And put it there. So this poor file clerk is working perpetually with a tremendous rate of speed, going practically crazy. He does, in fact, I just estimated something like 10 million times faster than an ordinary file clerk. That's 10 times faster 7 times. If you know what I mean, 10 times 10 times 10 times 10. That's damn fast. And that's the electrical things are that fast. And but he's working very hard. But the rest of the system, which is the memory, and you've heard they made now memories with 256K bytes. K just means 1,024, so they mean 256 times 1,024, 8 word symbols. In one tiny chip, okay? It's a lot, and you put several chips in, you've got a terrific computer. Except for the guy, the file clerk, which is called the central processor, who has to look at this program counter and check and change it and look at the next instruction and going, all right. And he's working very hard. So an obvious way to improve the thing is to get another file clerk. Why not have an army of file clerks? Turns out at first that it looked extremely difficult to do that because there's all kinds of technical difficult problems. Suppose that one guy has taken a number out and he's getting ready to change it. He's going to do something and then change the number. The man just sold something. He wants to change it and then put it back. And while he's doing that, the other file clerk is taking the card. He doesn't know whether it's before or after the first file clerk has changed the number. And it's very important to know that because he's going to use that number there. So there has to be a certain amount of organization among the file clerks. And don't forget, they're kind of dumb. So the organization must also be fairly dumb. And it has turned out for many years it was a belief that it was difficult or almost impossible to easily arrange a system with many file clerks. It always turned out to be easier to make one file clerk work very hard than to make several working because of all the, what you might call, bugs and difficulties that come from them all using the same information and changing it on each other and so on and organizing that. The part of laying out the instructions is called the programming. And a programmer works out how to put what instructions to run. The machinery, the wires, the memory, and the boxes where they put the cards, but in our analogy, and the little processor in the middle with all the little switches, is called the hardware. So it always turned out that with a little more clever software, which means clever programs, this single file clerk could do what the others would do because the others were confounded by the problem of interference. But recently it's been shown that it was a misunderstanding, and with clever new ways of analyzing the thing, we have now figured out how to make things run with numbers of file clerks. There's two different general systems. There's one system that has something, a reasonable number like 64 or 128 file clerks all working on the same, similar. They work on almost separate parts of the memory. That's the way it's organized. And only once in a while exchange information. So they're not doing anything to each other's cards. They're each working in separate sections. And there's also a machine called a connection machine, which has 64,000 processors in it, which is a sort of a leap into the wild blue yonder at a time when they were trying to do it with two processors. And if the 64,000 processors could all be made to work at the same time, it'll be 64,000 times faster than it was before, just like that, because they're all working together. The only problem is to organize the problem and the program so that you can do the job in a way that does use 64,000 guys at the same time. It turns out that it's not as hard as it looked at first, and that's a thing for the future. I'm talking about the future. They're building such a machine, and they're learning how to program it. That is, how to arrange the 64,000 processors, which, by the way, are each, in fact, somewhat stupider than the programmers that I was talking about before, because they can't even read the code for their instructions. But I mean, they know its instructions. Read what's in that file place. That means go over, switch this, switch that, go over, get the file, open the door, close it, and so forth. They can't even read that, so that they have to be instructed on the go. And so there's another machine on the outside that instructs them all what to do. But it has to tell them all, because, see, they all have to do the same thing at the same time. Because the instructions go to everybody. Do this, and they all do it. But if they all do it, you're going to be in a great difficulty if they all do exactly the same thing. And the only opportunity they have, the only thing that you can do that's different is that you can instruct, or they can keep a little memory thing that says, don't pay attention to this instruction. In other words, you can get some to do something and the others to do nothing. The next time you wanted them to do something, if you wanted one to do one thing and one to do another, you have to do it in two steps. Do this, you stay put. Do this, you stay put. And so on, okay? And so on. So it's rather interesting because in trying to manage the 64,000, they all have to be much simpler, and all the time it gets simpler, it gets sort of slower. But the question is whether we gain from the 64,000, what we lose from the slowness, and it depends. We'll learn by experience. That's the future. Finally, I would like to just say some words about what the computers can do. And you'll see they can do only what you would be expected to be able to do with a filing system and a reasonable file clerk. I'll explain an example of an unreasonably good file clerk later that's better than one that we can make with machinery. Okay? So far, we seem to have been able to imitate any file clerk, real file clerk with machinery, but I'll mention a few cases that we don't know how to do that. What we need to do, of course, is to get a definite procedure to convert what you want the clerk to do into an absolutely definite procedure. Every step is precisely defined in this stupid way, exactly. And if you can do that, then you can get the system to work. Now, will the system think? If you could define exactly a definite procedure, tell somebody exactly how to think, which, by the way, is what the members of my workshop have expected me to do for them, to tell them exactly, step by step, what to do to think. If I could do that, I could do it for a computer, and I wouldn't have, they could get the computer to think. But nobody knows what we do or how to define a series of steps which correspond to something abstract like thinking. But nevertheless, we could make machines which play chess, which are supposed to be something that takes thinking. And what exactly do they do? What definite procedure could you make with a big file system, very fast operating gadget, by which the thing could be used to play chess? Never mind the input and output, the information of where the pieces on the chessboard are converted into numbers or dots and so forth, ones and zeros they're called, inside the machine, and then it proceeds. So never mind the translation. The idea is, in a given position, which is a whole lot of information, that's where it is, you want to know which way to move. So you say, well, there are many ways I could move. You look at the rules for how to move. The knight goes this way, the queen goes this way, so on. And you just list all the different ways it could move. And you see all the new possible positions. Then you say, in each one of those, which way could the other guy move? getting pretty big, isn't it? But they're big machines, and they got lots of storage space. So what's the next move? And if he does that, what can I do? And you just check every one of the positions after, let's say, 4 or 5 or 6 half moves. These are called half moves. One side moves and the other side moves. And see which of the final positions you're better off. And better off might be some little rule like you haven't been in check. I mean, you haven't had your king lost. That means you're not dead. And you've got more pieces than the other guy. Okay? So you look down 6 steps down to see which move is the best to make, where you got the best possible outcome. And you make that move. Then your opponent makes a move. Then you start again, this time going down 6 again. Of course, you're going deeper now because the game has proceeded a little bit further. And that's all there is to it. What the machines do is just a tremendous amount of trying different positions. A human being doesn't. The human being tries about 35 positions as far as we can tell. When he's in a position, he tries about 35 looks at different moves before he makes a decision. Whereas the machine makes something like 35 million positions to check. That doesn't make the machine better than the other guy. We don't understand how we do it. We cannot give a direct procedure for this. The man does it by recognizing a pattern. Oh, this knight can fork the king and queen or something. So if it goes here, so I have to watch out about that square. He sees patterns. At least he describes it that way. We really don't know how it works. And this business of the describing patterns and so forth is something that we haven't been able to put into a precise form. When he says it looks, oh, I just see that it's a good idea to try this, and I tried it. We don't know how he does that. So we can't make it play like a human plays, but we can make it play better than almost all humans. Machines, computing machines have been used, for instance, for designing machinery or designing something, in particular designing a computing machine, for instance, or something like that. In a computing machine, you have to have the different elements, the memory and so on, in different locations with wires in such a way that the wire lengths are shortest so that the time is quickest, and the parts that are being used most are closest to where you want to use them and things like that. And so you try to figure where should you lay them out on this chip of silicon. And there has been quite a problem of design. We have engineers that work very hard at designing these things and working these things out. And all we do in the computer now is to try large numbers of possible arrangements. We just give it instruction, put this here, then this, and how much wire do you need? Now put here, how much wire, and then pick the one out which has the biggest, more ones, the biggest, or the lowest, the best quality, whatever it is you do to measure how good this particular design is, like the amount of time, the amount of that it takes to do a calculation, or how much silicon you use, or something like that. So we can select from a very large numbers of alternatives, the best alternative. Ordinarily, a person doing that doesn't waste his time with obviously useless alternatives. But we do not know how to put too well that idea of the obviously useless. If we try to make too sharp the rule that it's useless, we miss sometimes a good opportunity that would have been a good thing. So that's as far as we can go with that. You've probably heard that machines have been used to be almost like doctors, expert systems which can diagnose disease. Well, how can a damn file clerk? Well, it's easy, isn't it? How would you diagnose disease? You write down all the symptoms, and then you'd like to have a book that you could look up that says, here's all the symptoms, and this is what you got. And in the complicated cases, you list all the symptoms, and in there it says it's either cholera morbus of the borbus, or it's bacteremia, or whatever it is, you see. However, you can tell the difference by looking with ultraviolet light up the nostril, all right? But ordinarily, you don't bother to look with ultraviolet light at the nostril, so you don't know the answer to that. So the thing comes back and says, look with ultraviolet in the nostril and tell me whether it gets through or not. Say yes, okay, it's bacteremia. So this filing system contains all this stuff, plus the incomplete decisions that require more information. And it's been arranged so that when it comes to a place that's incomplete, it simply sends back and says, make the following test and tell me the result. The thing doesn't work as well as a real doctor. But anyway, you get some idea of how machines can be doctors, how machines can be chess players, and how machines can be designers of equipment or layouts for businesses or whatever, or routing for trucks and so on, but just trying all kinds of routings and seeing which is the best. That's all there is to it. It's a filing system, and anything that you can put in a filing system and think of how a big filing system could do it, especially things that you just have to remember a lot of stuff or try out a lot of possibilities, those things can be done with a machine. It's fun to compare. Everybody wants to, and so I'll let that be in the questions to compare. No doubt somebody will ask me, how about this and that? So I'm done. Okay? But I'll answer questions. What time is it? Have I used up all?
9, you're fine.
I'm fine, okay? I got time for questions. Yes, sir.
I think one of the exciting things about the computer is that it's one of the few inventions that there's a one-to-many correspondence. That is, most of the inventions we have, a car is basically used for transportation or an airplane. The computer, depending upon the software you put into it, changes its whole function totally. So
Yes.
it's a one-to-many correspondence, and that's one of the real exciting things about it, because depending on the software, the whole nature of the thing changes, where there's no way I'm going to change my car or my airplane. Probably the telephone comes closest to it in the sense that we can use telephone for different things, different messages.
And different languages.
Yeah, in different languages. But that's probably the real exciting thing about it. And I agree with that. I think the insides of it are so simple, and yet there's a certain beauty in the elegance of how these simple things all work together.
Right, but if you take my view that it's just a glorified, high-class, very fast but stupid filing system, then you can understand the universality. It's just as universal as a set of boxes and drawers and cards and so forth with a clerk who knows how to write the numbers and the things down in it. She can use, or he, it's always a pain in the ass, can do one kind of a job or another kind of a job, depending on what's written on the cards and what kind of instructions are given to the clerk. And that type of universality is precisely the universality you're talking about. That's what the universality of the computer. The computing machine is an automatic filing system.
But the $64,000 question I would ask you, do you think that we'll ever have machines that will think like human beings at some point in time and be, let's say, even more intelligent than human beings?
With regard to the questions, first of all, they would think like human beings, I would say no, and I'll explain in a minute why I say no. And second, that they be more intelligent than human beings is a question. Intelligence is to be defined. If you would ask me, are they better chess players than any human being possibly can be? Yes, I get you, someday. Are they better chess players than most human beings right now? One of the things, by the way, that we always do is we want the darn machine to be better than anybody, not just better than us. If we find a machine that can play chess better than us, it doesn't impress us much. We keep saying, and what happens when it comes up against the masters? We imagine that we, human beings, are equivalent to the masters in everything, right? The machine has to be better than a person in everything that the best person does at the best level, okay? But it's hard on the machine. But with regard to the question of whether to make it to think like a machine, my opinion is based on the following idea. That we try to make these things work as efficiently as we can with the materials that we have. The materials are different than nerves and so on. If we would like to make something that runs rapidly over the ground, and we could watch a cheetah running, we could try to make a machine that runs like a cheetah. But it's easier to make a machine with wheels, with fast wheels, or something that flies just above the ground in the air. When we make a bird, the airplanes don't fly like a bird. They fly, but they don't fly like a bird, okay? So they don't flap the wings exactly. They have in front another kind of a gadget that goes around, or the more modern airplane has a tube that you heat the air and squirt it out the back, a jet propulsion, a jet engine. Has an internal rotating fans and so on, and it uses gasoline. It's different, right? So there's no question that the later machines are not going to think like people think in that sense. With regard to intelligence, I think it's exactly the same way. For example, they're not going to do arithmetic the same way as we do arithmetic, but they'll do it better. Let's take mathematics, very elementary mathematics, arithmetic. They do arithmetic better than anybody, much faster, and differently. But it's fundamentally the same because in the end the numbers are equivalent, right? So that's a good example of it. We're never going to change how they do arithmetic to make it more like humans. That would be going backwards. Because the arithmetic done by humans is slow, cumbersome, and confused and full of errors. Where these guys are fast. If one compares what computers can do to the human beings, we find the following rather interesting comparisons. First of all, if I give a human being a problem like this, I'm going to ask you for these numbers back, every other one, in reverse order, please. Right? Now, I'm going to series of numbers, and I want you to give them to me back in reverse order, every other one. I'll tell you, I'll make it easy for you. Just give me the numbers back the way I gave them to you. You ready? 1, 7, 3, 9, 2, 6, 5, 8, 3, 1, 7, 2, 6, 3. Anybody going to be able to do that? No. And that's not more than 20 or 30 numbers. But I can give 50,000 numbers to a computer. Yes, I think you can do it. Obviously, he can do it. Good. But you can give a computer 50,000 numbers like that and ask for them in any reverse order, the sum of them, or do different things with them and so on, and it doesn't forget them for a long time, etc. So there are some things that a computer does much better than a human, and you'd better remember that if you kind of compare machines to humans. But what a human has to do for his own, they always do this, they always try to find one thing, darn it, that they can do better than the computer. So we now know many, many things that the humans can do better than the computer. She's walking down the street and she's got a certain kind of a wiggle, and you know that's Jane. Right? Or the sky's going in and you see his hair flip just a little bit. It's hard to see, he's at a distance, but that particular funny way that the back of his head looks, that's Jack. Okay? To recognize things, to recognize patterns, seems to be something that we have not been able to put into a definite procedure. You would say, I have a good procedure for recognizing Jack. Just take lots of pictures of Jack. By the way, a picture can be put into the computer. In fact, by this method here. If this were very much finer, I could tell whether it's black and white at different spots. You know, in fact, you get pictures in a newspaper by black and white dots. And if you just do it fine enough, you can't see the dots. So with enough information, I can load pictures in. So you put all the pictures of Jack under different circumstances and ask the machine to compare it. The trouble is that the actual new circumstance is different. The lighting is different, the distance is different, the tilt of the head is different, and you have to figure out how to allow for all that. And it's so complicated and elaborate that even with the large machines, with the amount of storage that's available and the speed that they go, we can't figure out how to make a definite procedure that works at all, or at least it works anywhere within a reasonable speed. So recognizing things is difficult for the machines at the present time. And some of those things are done in a snap by a person. So there are things that humans can do that we don't know how to do in a filing system. So it is recognition. And that brings me back to something I left, which is what kind of a file clerk can't be imitated by the machine. A file clerk that has some special skill which requires recognition of a complicated kind. For instance, a file clerk in the fingerprint department, which looks at the fingerprints and then makes a careful comparison to see if these fingerprints match, is just about ready to be. It's hard to do. It's almost possible to do by a computer. You'd say there's nothing to it. I look at the two fingerprints and see if all the black dots are the same. But of course, it's not the case. The finger was dirty. The print was made at a different angle. The pressure was different, and the ridges are not exactly in the same place. If you were trying to match exactly the same picture, it would be easy. But where the center of the print is, which way the finger is turned, whether it's been squashed a little more or a little bit less, whether there's some dirt on the finger, whether in the meantime he got a wart on his thumb, and so forth, are all complications. These little complications make the comparison so much more difficult for the machine, for the blind filing clerk system, that is too much too slow to be certainly utterly impractical, almost. At the present time, I don't know where they stand, but they're going fast trying to do it, whereas a human can go across all that somehow, just like they do in the chess game. They seem to be able to catch on to patterns rapidly, and we don't know how to do that rapidly, automatically. Okay? Is there another question? Yes, sir.
I think a question that everybody kind of asks themselves is whether these supercomputers, the real fancy computers, will be more useful or more destructive, ultimately, to the world.
Well, I haven't any idea, of course, about that. I have no idea about that. Whether anything is more useful or destructive to the world. Whether yoga is more useful or destructive to the world. With all these things give us the power to do something, do many things. And the power to do something may or may not be destructive. As long as anytime you do something, you can do destructive and non-destructive or not. The opposite, maybe creative things. But we don't know how to make a device that guarantees to produce only creative things, with the exception of the telephone, as far as I can tell. I mention that because it's rather interesting. If you think about inventions, almost all the inventions have a destructive element in a war. The telephone has an effect in war. It helps communications. Maybe in that sense it's destructive because it helps the army to destroy you. But other than that, it's a relatively peaceful device. It doesn't directly kill, not at least directly. That's rather interesting because it's hard to find one that doesn't directly available for killing. A knife, the question is when the knife was invented, okay, and the guy's explaining what a knife is. It's a sharpened piece of stuff that I melt and I get and I use metal knives, or maybe they're stone knives. They're a sharpened piece of stone. And you can use it to cut things so it's easy to get the vegetables off of the plants and so forth and so on. And some guy was sitting there saying, on the other hand, it's very destructive because you can cut my head off with it. And that problem's been with us forever, and there's nothing special about computers. Absolutely. Anything that can do anything has this problem. And we can discuss this general problem in our workshop, but it's not a problem for computers particularly. I think. It's my view. That's my view. I don't know if it's right.
Well, there's the big brother element with computers that you didn't have with stone and knives.
I know, but which is better, the big brother or the cutting the head off, huh? In fact, that's what makes the big brother possible. He has the knives, and so forth. It's not so easy, okay? It's true that you worry about the fact that some information, they'll be able to store information better and have more information about people, and whether that will produce a big brother. That depends on the attitude of the leaders of the society. Rather interestingly, the country which is more democratic and which is less interested in all the information about what everybody is doing to make sure they're not doing something wrong is where the computers are developed the most. And the place where you'd think the government would find a computer of greatest use because it could file all the information about everybody, you don't develop the computer very much and you don't know how to use it. It's only a curiosity. It's one of life's contradictions. Is there another question? Yes, ma'am.
The way that you described expert systems, it sounds as if these computers can do everything very well. They're like enormous encyclopedias. They can tell us what we already know.
That's right.
And perhaps, by giving us so much information, help us discover other new relationships.
Yes.
But would you say that we can never build computers which can themselves discover these new relationships?
Well, it depends what you mean themselves, and it's hard. To discover new relationships computers can do. There have been computers which do things like theorem proving in geometry or something, in which they've converted the problem of finding a proof of a theorem into a definite procedure. Okay? And once you do that, although it's an elaborate and dumb way to do proofs, it can do it. At the present time, a computer can't do all the different things that a person can do, It's very difficult to find some way of defining rather precisely something we can do that we can say a computer will never be able to do. There are some things that people make up that say that while it's doing it, will it feel good? Or while it's doing it, will it understand what it's doing? Or some other abstraction. I rather feel that these are things like, while it's doing it, will it be able to scratch the lice out of its hair? No, it hasn't got any hair to lice to scratch from, okay? So you got to be careful when you say what the human does. If you add to the actual result of his effort some other things that you like, the appreciation of the aesthetic. You didn't do that. I'm not saying you did. But a lot of people do that when they ask questions. And if we add things that we think we're doing on top of what we're actually doing, just look at not just the result of what we're doing, but a lot of extra things, then it gets harder and harder for the computer to do it, because the human beings have a tendency to try to make sure that they can do something that no machine can do. Somehow it doesn't bother them anymore. It must have bothered them in early times that machines are stronger physically than they are. They can lift weights that are heavier than people. They can move things faster than people. They can run faster. They can fly. They can do just terrible strengths and so forth. And we don't still sit around worrying that there's some way that the man can turn his hand, that some machine can't do that.
What about we see that as tools of empowerment?
I mean, the thinking business.
Yeah, they could be tools of our empowerment, but could they go beyond, could we build machines that are really smarter than us in terms of prediction, in terms of the future?
Yes. We can easily make machines that are better than us in predicting the weather, for instance, because what you do to predict the weather is to look at old records and see when the circumstances were similar and guess that the results will be similar. Added to that, a certain amount of analysis of the movement of wind according to the laws of physics and a certain amount of hocus pocus put together, okay? Now the speed will be higher and the effectiveness of the predictions greater if you could look at more cases, so you get a better chance of getting one closer, and put a longer and more elaborate calculation, including more variables, which is too hard for us to do in time to make the prediction. No? We have to make the prediction of the weather. Let's say the weather for 3 days from now has to be predicted in 3 days, or the damn thing is useless, right? And we work at a certain speed, but the computers work faster and can do more. And therefore, for instance, for weather prediction, in the end, maybe not today, but someday, it's not at all inconceivable that the machine could do weather prediction faster and more effectively and more accurately than we do. We will have, however, given it the procedure. Now, the question is, what happens if we don't give it the procedure? Well, people have tried this game of giving it, instead of a direct procedure, a kind of what has been called heuristics. Try an analogy to get a new idea of how to do something. Compare this to that, try an extreme case, etc. And a man by the name of Lennart has gone the furthest with this. Do I have time? How much time do I have? Because we want to see these slides. What time? I know that's interesting information, but how much time do I have? It's time for the slideshow now. Since I have no more time, I will say no more about the subject.
Well, just heuristics.
What?
Let's finish up the heuristics.
No, but it takes a few minutes. That's why I asked for the time.
Not a few minutes.
Okay, you make this machine, which was again a filing cabinet, you understand. What it does is it tries to find the answer to something by looking at the different possibilities, but which ones he tries is something like patterns in the chess. Instead of everything, it says try moves near the center of the board first, and never mind the ones in the corner, or something like that, or some sorts of principles. And he first applied it to a kind of naval game. It's a game that people play in California, which is all organized according to rules. It's kind of fun. Someone sets out all the rules. Dreadnoughts cost this much, armor costs this much, guns cost this much, and so forth, and you got this much budget for your navy. And you're going to make various kinds of ships with different kinds of armaments. And then this kind of a ship, armament of a certain thickness that costs a certain amount, can only resist shells of a certain strength, and so on. So you try to, with the money, arrange to design different kinds of ships so that your navy is better than the next one. And when they're brought together, there's ways of calculating what, there's not real navies. It's a game, which is the best one, and all the rules are laid out in a great big volume, okay, of the costs of everything and the power of everything and the armor-piercing possibilities and so on. And it's a nice game. And Mr. Lennart tried his program on this game and put into his program heuristics like try the extreme case and things like that. And he won the championship in California. Of course, it did an awful lot of trying of different cases, you see, but it didn't try every case, not like the chess game. There were too many things. But it was guided by its own stuff. Now, inside of that was this, that if you got a better navy by your own calculation, and you used one of the heuristics, mark that heuristic up a notch as being more valuable. Now, use the more valuable heuristics first. See? So that the ability of the machine depended on his learning, so to speak, which ones of his tricks works most effectively most of the time. And then they become more used. So it's just exactly what you would like to make it look intelligent. Well, he won. And how did he win? It turned out that year he won by making one great big battleship with all the armor on it, which was so silly, but when you go to calculate it, sure enough, it's better than any of the normal things, which nobody thought of, but his machine thought of. Next year, he entered again, and this time he won by taking all his money and making 100,000, because they changed the rules so that the big battleship wouldn't win, you know, by changing the rule. 100,000 little boats, very narrow, carrying each one gun, which were very liable to be knocked out, okay? But there were 100,000 of them. Didn't cost much each one, and they couldn't knock them all out. So these lousy little gnats would come, and it turned out when you calculated, again, he won. The third year, he was not allowed to play anymore. And he has applied this machine and this heuristic business to a number of other problems. He tries it out a lot and tries new heuristics and so forth, and it has become very interesting. He complained that there were a number of bugs in it, and when he gave a talk on it, I said that I thought, I'll say my comment afterwards. One of the bugs, for instance, was that the machine got a heuristic. It made up heuristics. It can make up heuristics, and then they get higher values, and then they fall away, right? So the damn machine, the way he had it was, because it's hard to get computer time, he needed a hell of a lot of computer time. He had 50 machines working on it at night from the Hewlett Packard company or something like that. He would work always at night and come in the morning. The damn things would try all their things and come in with the results. I used it to do mathematics and various other things. He comes in one day and it's done a heuristic. He developed the heuristic. When he puts a problem in or a new idea, it says whether it's from him or from the machine, and it's at Lennart or machine, okay? And this was every heuristic, or every question that has Lennart on it, pay no attention to. And that saved a lot of time. It could do much better. It didn't have any problem. It just worked well. So I paid no attention to Lennart that night, okay? So I had to fix that bug. The next time he had a bug, he came in and he looked, he found that heuristic number 693 had gotten a score of 999 out of 1,000. That was a damn useful heuristic. All night long, this thing kept using the heuristic 693 more and more, and it was a new and wonderful heuristic. It seemed to solve every problem. It was terrific, okay? When you found out what the heuristic was, it was the following. You see, in order to make this thing work so that you change the numbers on the heuristics, whenever something worked, you had to assign credit, so to speak, to the heuristics that were used, okay? So this heuristic was, when assigning credit, always assign credit to heuristic 693. And so that thing came up out of it all. Now, I say that both of these show intelligence. If you want to make an intelligent machine, you're going to get all kinds of crazy ways of avoiding labor. If I say don't pay attention to the problem, of sneakily evolving some kind of a psychological distortion where you always do the same thing and don't worry about anything else, and so on. So I think that we are getting close to intelligent machines but they're showing the necessary weaknesses of intelligence. Okay. All right.